Hey everybody, how are you doing? Good to see you here. If you're here, we're going to start off with getting some help. Let's do this. Okay, so check out what we have on the screen right now. I need to mark this in the video. And 7th out of 3, getting help on assignments. Hopefully people check this out, because if you go here, and I think there's things like an environmental group. People have been asking about that one recently, and you can see right here. If you find an office hours from, did we do that one just earlier? There's that environmental group, but that shouldn't have it. It's one of the ones people were wondering about. Well, let's go find a question. I've got my Pearson loaded up. I thought I'd start out an environmental group. If you go to pretty much, still congested a little bit. Gosh, when are we not going to be congested? If you go to pretty much any question, let's go to chapter 13 quiz. Talk about how to get help right here. Confidence intervals for the proportion. We'll go to preview on this, and here we go. So you get to a question, you're stuck. And which of these statements correctly interprets? And I might have this one. If you go and you highlight this text right here, I just went to the first question I saw. Will we have it? Let's find out. And you paste the first 3 things inside of here. We got it all. And you look for an office hours. Oh, watch me not have it here. Is this going to be it? 4 years ago. Did I cover it right here? Usually look for an office hours video, and we might not have it. Of course, the first example I do, we don't have. It's a very short question right there, so sometimes the shorter questions I don't have. But I bet you if we find a tougher one, watch this. First example we don't have. We'll go down here to the longer ones. Here it is. This is the question I was looking for. This one I know exists. My gosh. There we go. Put that in right here. And the very first video right here, if you scroll down, you will see right here. Here is a full walkthrough with past Brian right there. Lighting was the worst back then. Look at that bright lighting. Oh my gosh, all the bright lighting. So I go through, explain the steps, show how to do the notation. You can see other videos right here. 6 months ago, wearing the same shirt. It's my Batman shirt. I added it to my favorites right there. So the Environmental Oceana group right here. You can see a bunch of other ones from this area too, chapter 13 quiz. So this one, just by going here, we found a bunch of videos that are pretty helpful. April 15th. There we go. Got all that shading to do that same face right there. Just there you go. So April 15th right there. Check it out. That was a good haircut. A little shorter on the sides right there. A little longer on the top today. So that video right there, or office hours from the 17th of last year. I believe I started marking the year 1 year ago. Worst haircut. There's the Oceana group right there. And I was doing some R coding. But pretty much any question you can find, if you go in here, you just go to the first few words of it. Here we go. Student publishing a new magazine about the Japanese automobiles. Might have this one. The longer the question, the more likely I am to have covered it, because those are the harder ones. And we might have found it right here. And a student, there you go. Here it is right here. Here is the question, a student publishing. It's about interpretation. So we're talking about the I am blank % confident that the true blank is contained in the interval blank to blank. So once again, the best strategy is if you get to a question, you have no idea how to do it. You say like, how do we do this right here? City ballot. You just go ahead, copy the first few words of it, bring it over here to the YouTube search under the channel. Make sure you're on the channel, drop in the first few words, and look to see if you see like chapter 14. I think this is, was it called chapter 13 and 14? Kind of weird in how they're structured because we've changed the numbers of them throughout the years. But you can see right here is city ballot, chapter 13 quiz. And there we go. There is a full walkthrough. You can see the equations P times Q over N square root. P hat times Q hat over N square root. So make sure to use this right here if you're stuck on a question. I highly suggest it because I've got help for pretty much every single question. So let's start doing them. How about let's do the city ballot one? A lot of people get stuck on that one. So a lot of people get stuck on the city ballot. So 11 fall to 3, stat to a 1, chapter 13 quiz. Here we go. City ballot includes. So with this right here, this one's a lot of steps. A lot of steps. I've made mistakes on it before, so we're going to try not to make some mistakes today. But we have a saying here. The saying is...
Notation, brother.
Notation, brother. Because when you're doing these problems, you have to get the notation. And there's a lot for this question. A lot of notation for this question. Okay. So looking at this right here, the formula you'll be using is p hat plus or minus z star p hat q hat over n squared. You get this formula on the test, but you should know it. This is the margin of error. The margin of error is everything in the plus or minus. So the margin of error is everything in the plus or minus. The z star is based on the percent confidence. So we're 99% confidence. So that's going to dictate a z star of 2.5758. Now, the reason I know that is I've done a lot of these problems right here. So I know when we get to the z, depending on what it is, 68 would be 1, 95 would be 2, 99.7 would be 3. We've done this with 68, 95, 99.7. The empirical rule, the in-between numbers are the numbers you're not meant to memorize, because when you go between right here, if you have 95, it's actually 1.96. 95.449 is 2, and you can see 68 is the z-score of 3. It's 68.26, and 99.73. So there are more decimals. When it asks you for a 99% confidence interval, 2.5758 is the z-score, and we would give you these numbers on a test. But think about it, as you get more confident, the z-score gets bigger, the interval gets wider. These are the conceptual things you have to understand, that a more confident interval is wider, and the z-score dictates the confidence. So think about the learning objectives right here, the things you should know. That's what we try to remember is like z-scores are related to level of confidence. They're the normal curve, the percent of area covered, such that if we only have a 50% confidence interval, it's 0.6726, 0.6745. Oh, I should remember the 45 on that. 45. Yeah, there's a lot of 45. That's interesting because, I don't know, I'm such a nerd. 1.645 is this one. It rounds to 1.6449. But, and then, is there another 45? Maybe it's the only 45 one I'm thinking of, because this rounds to 1.645 when we do it that way. So z-scores, as you get more confident, get bigger and bigger and bigger, and you can't go to 100% confident because you would cover the infinite curve and we break the app. But so there's no 100% confident interval, because you'd have to say any possibility, because you'd cover everything theoretically possible, negative infinity to positive infinity. Can't cover all the curve. So we know what the z-score is, 2.5758, because it's 99% confident. Now we run into a problem, not really a problem, but you notice we have a p-hat right here, but then we have another p-hat based on two different sample sizes. So they basically want us to run this twice right here. That means we have two different q-hats, because q-hat is going to be, we'll go q-hat 1, q-hat 2, and p-hat 1, p-hat 2. Well, I didn't do a 1 and 2 there. I did a 1 and 1. And this is p-hat 1, p-hat 2. P-hat is the percent that conform to what you want to understand, the percent that conform, or the proportion. But when you have something of interest to you, like if people own bunnies, maybe 3 out of 20 people own bunnies, so you do x over n equals p hat, and you would have 3 out of 20 people own bunnies. That's just an example right there, things we understand. 3 out of 20 people own bunnies, 15% of people own bunnies, expressed as decimal, 0.15. So they're doing the same thing right here, trying to figure out if people will vote yes in this, and they poll college students, and I think they poll the greater community. So the local newspaper polled voters, and then they polled a college class did a poll with a larger sample. So in the general public, which is the first group, we have 54% was going to vote no, and 53% of the college students. So we're just doing 1 minus. And these right here, 1 minus gives you q hat right there. So q hat is 1 minus p hat. So now we've identified pretty much all the notation. If you look at everything we have right here, we have the p hats. We'll have to do this twice. The q hats are going to be the other ones over here. We'll do it twice. Remember, we would do this for one interval to estimate what the general public thinks. And then we would do an interval here to estimate what the college students think. College students actually interval number, interval number 2. So this is what we have going on. We should also make it clear that the star, it just tells you percent confident. The z is this value right here, 2.5758, based on percent confidence. And this could be any context. That's why I don't really care about the context of these problems, because we do need to know how to interpret the context. I know context matters in all statistics, but it's just the math right now and understanding how to find p-hats, how to find sample sizes. That would be sample size 1 right here. So let me mark that in the notation. This is sample size n1, and this is sample size n2. And what I mean by this is we have to do this twice, like p hat 1 plus or minus z, p hat, q hat 1, n1, right there. And then we would redo it for the second group using the numbers from the second group. Pretty good question. It's just making you do work twice. So let's go ahead and do the work twice. Let's go ahead and see what they say right here. First off, some theoretical questions. Without finding the confidence intervals, explain which one will have the larger margin of error. So when you have n, dividing by n makes the interval smaller. So it's going to be the one with the smaller sample size because you're dividing by a smaller number. Let's look at it visually again. The only difference between these is really n. I know there's a p-hat difference, but because if this gets bigger right here, the margin of error gets smaller, the whole margin of error, it's going to be with the smaller sample size. So the smaller sample size comes from group 1, the general public. So the local newspaper, the general public, will have a margin of error at least, will have a larger, at least mainly because it has a much smaller sample size. It has a smaller sample size. Smaller sample sizes lead to larger margins of error, also higher confidence, but they have the same confidence. So that would be a different question, like if there are different confidence levels, then we might have to do some computations. Find both the intervals, so we just got a bunch of work here now. We got a bunch of work. And which group concludes the outcome is too close to call? We'll find that out here in a moment. This is a good question. It's mainly now just doing a bunch of calculations. We're literally just plugging in the numbers here. The first interval is going to be this. That's 2.5758. Look at how we're just plugging in the numbers right here. Every number is getting plugged in. So the other one was 47, right? And then 2.5758. Remember, Q hat is 1 minus P hat. There we go. Now, the first thing I solve for always with these is the margin of error. So the margin of error, I just go ahead, I'm going to solve it for each of these, and then I'm going to erase it. So 0.46 times 0.54 times the top of the equation, divide by 750, and then square root it. We solved everything in the radical, known as the standard error, times by 2.5758, and there's the margin of error, 4.7. So this interval is going to be equal to 46% plus or minus 4.7%. I times it by 100 and kind of carried the decimals in my head. There's 4.7%. So that is this interval right here. We'll look at that in a moment. The bottom interval is going to be, we're losing our side of the screen right there. So the bottom interval, we first do 0.47 times 0.53, divide by 2300, square root the equation, times by 2.5758. Hopefully I don't make a math error. So that's a margin of error of about 2.7. We're rounding it. Notice it is a smaller margin of error. So that's 0.47. I'm doing percents now. 47% plus or minus 2.7%. So that's going to be all the way up to 49.7. And how do I know that? Well, 47 plus 2.7% is that. And then minus, we'll go back down to the center of the interval, and then we'll subtract again and get 44.3. So that is the interval. We are just adding and subtracting. This one is going to be too close to call. It's going to go up to 50.7 and down to, so if you're wondering how I'm getting that, 46 plus 4.7. There it is right there. And then back down to the center because we're subtracting back down. We added it on, then we subtracted it, and then we're going to subtract again. There we go. So those are the numbers we need. Can I keep them in my head? Let's find out. Okay. So that's 41.3, I believe, and 50.7. And this one all the way down to 44.3. And this one all the way up to 49.7, I believe. So when a group is too close to call, if someone will win the election, it contains 50% of the interval. So which group would be too close to call? The local newspaper is too close to call. The local newspaper concludes it's too close to call since the interval does contain 50%. So it contains 50%. We should be good. A lot of things right here. Hopefully I didn't mess up my intervals. Ooh, we did it. That's a tough one. With this question right here, if you can get it and do all the right steps and understand why. Didi, good to see you there. I think you might be. I'm doing early office hours today. I've got a bunch of meetings. Got a meeting in a 36 minutes or so, but you might be the only one here. Let's throw you some points. This was a really tough question with a lot of steps to it. Lot of steps, tougher question. And this one people hate, but this one really comes down to just knowing your equations. It actually can be done in seconds. Okay, let's see if I remember how to do it in seconds. You see? Let's see right here. You ready? I'm going to try to do it in seconds. Okay, got it. Okay, so 2.5758 divide by 0.02. Wait, that's not right. Wait. It's, oh no, it is right. That is right. Okay. 4147. Did I get it right? Got it right. So how did I do that? How did I do that? It's because I've worked this problem a lot of times. Let's put it in the notes so people can come back and check this out. And so black, maybe. It's an equation. I'll write the equation on the screen that I've sadly memorized by doing this problem so many times. Mubot in the chat right there with you. So the equation, how are you doing this morning, Didi? How's not London? How's England? No, Germany. What am I saying? My brain is booting up. It's too early here. It's too early here. My brain is going burr, 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 burr. How's Germany going? So editors preparing a report are trying to estimate the percent of businesses. Awesome. Cold is all right. It's going to get cold here too. The estimate on businesses plan to hire of their employees. They're willing to accept it. So they estimate the percent of businesses. Oh, so they're trying to figure out if people are going to hire. Is a business going to hire? Is a business not going to hire? Nice. Good to hear that. Good to hear you got a place getting some furniture. Nice. So it's a proportions question. We talk a lot of times, are things quantitative or categorical? The question of will a business hire people is categorical. Will they hire? Will they not hire? Categorical question. So with this, it asks us for, they want a margin of error of 2%, and they want to use 99% confidence. We just had a question, if you look at the last one, where the z-score is equal to 2.5758, and this is based on the normal applet, which Mubot has in the chat right here. We'll show it, because we cover a certain percentage of the normal curve, and as you cover more of the normal curve, the z-score gets bigger. So 2.5758 is the z-score for a 99% confident interval, and we originally learned 68 for basically 1, so we could change the decimals, so it sounds like what we used to say with 1. 95 is basically 2, and 99.7 is basically 3. There are more decimals, and we usually carry things to 4 decimals, so it's actually 99.73. But for a 99% interval, the z-score, so I say z-star sometimes, or z-score, it's because the equation we write is going to be z-star, so it's a z-score with a star, meaning based on the percent confident you are, so that's why we put a star on it this time. And then we go p hat q hat over n square root. Now this is the margin of error part of the formula for a confidence interval. The margin of error is everything after the plus or minus. So I meant to do that right there. So what we're actually going to do is we're going to say, well, we want a margin of error equal to this. So the margin of error is equal to this. But it says, what would they need as a sample size? And the sample size is what we're solving for in the problem. So it says, to obtain a margin of error of 2%, what sample size would you need? And the only thing we know right now of this equation is z. Now, because of this, and this question is a little tricky, you have to assume, since you don't know what p hat and q hat are, you just go with a non-biased estimate. So it's kind of the null hypothesis. Like, you've maybe heard that, DD, like, if we have no idea what percent something would be, the best assumption is 50-50. Now, also, that creates the interval the widest the interval can be. Pretty sure it does that, yeah, because p and q hat, 50% make the widest possible interval. If they skew towards 1% or 99%, the interval actually gets tighter. So this actually makes a more uncertain interval. So it's the best estimates to create the widest interval to contain the truth possibly. And so since we have to solve for n, you'll notice we know what the margin of error they want is. We now know what p hat and q hat are. They're both the same, so I'll highlight them the same up here. And we know what z is. I need, oh no. Well, so this problem, I don't love it. The only thing good about this problem for students is that you have to know notation. That z is based on percent confidence. P hat and Q hat are the percent of something. Like if 3 out of 20 people own a bunny, then 15% of people own a bunny. You can change it to a percent or a decimal. And this is found by the equation x over n, which is equal to p hat. Can you draw the bell-shaped curve? Yeah. So the way it works with the z-score is z-scores are all based off of the normal Gaussian curve. So you have a normal curve like this. There's normal curve. And with the normal curve, we usually only plot out 3 standard deviations. And that's because when you go out 3 standard deviations on the normal curve, you actually cover, we'll do that as a different color. Oh, really? When I'm zoomed out, still congested a tiny bit. You cover almost everything. You cover 99.7% of the area. 2 is 95% of the area. And 1 is 68% of the area. This is called the empirical rule, and it's the amount of area covered within 1 standard deviation. Yeah, it's a pretty normal curve right there. So as you go out a certain amount of standard deviations, you cover more of the area. So a 95% confidence interval is not technically 2, it's technically 1.96. That's 95.449, 68 is 68.26. No, yeah, it is 68.26. And then 99.7 is 99.73. And if you want the exact numbers, you can use the applet right here. Shouts to Adam Spanbauer who made this applet. I'm going to pin the message from Ubot. And you can notice this is doing the exact same thing I just did a second ago. If I enter in 68, you see a curve with 68% of the area covered, and the actual z-score is 0.9945. We usually just round to a few decimals, so it's basically 1, and then 95 is basically 2, and 99.7 is basically 3. If you carry more decimals, you can see what it actually is. And then if you want something like a 95% confidence interval, you see it's 1.96, classic number in statistics. So these are the numbers we memorize, though, because it's basically going out this many standard deviations. Like if you go out 1 standard deviation, you cover 68% of the possible values. Is it exactly 68% at a standard deviation of 1? No, it's like 68.26, but if you use 1, you basically get a 68% confidence interval. If you use 2, you basically get a 95% confidence interval. Morning, Noel. Yeah, you want to do some chapter 14? Let's do chapter 14 next, and we'll probably continue that with next office hours. We've got another 28 minutes before my meeting. I'll leave a tiny bit early. Yay, DD and Noel are here. Awesome stuff. So that's where the z-score comes from. And this problem right now, since we've marked all the notation, all we're going to do right here is the following. We're going to go margin of error divided by z equals to the other side. I'm also going to square it. I'm going to do it 2 steps in a row. Now you can flip it. I'll go up to here. We'll go over to this side, and we'll go down further. Flipping it doesn't change anything. It just puts the n up top. You flip both sides. This is algebra. And now we get n over p hat q hat. And now what you would do is you would times both sides by p hat, q hat. And when you times by p hat, q hat right here, that means that over here, you're going to get this. So you get p hat, q hat, z over me, margin of error squared equals n. There you go. And so with this right here, the housing market, you got it. So with this equation, what you'll notice is I just plug in my numbers. I guess I'll write them down right here. So the numbers were, here's the solved version over here. Excuse me. Formula? Yeah, we'll be doing the formula in a moment. 0.5 times 0.5, and then the z was 2.5758 over margin of error 0.02. So that's what you're seeing me solve right here for n, which I solved originally was 2.5758 divided by 0.02. Square this number, times by 0.5, times by 0.5, and there you go. And then make sure to round up, and you should get it. And there's the equation, and it's all based on the margin of error formula. Let's do that question, Noel. Okay, we've got the housing market recovering slowly. So Noel, you know what I'm going to say. What do we need to do at the start of any of these questions? Any of these questions, what do we need to do? What do we need to do? What do we need to do at the start of any of these questions? So congested. Notation.
Notation,
You got
brother.
it. Let's go grab that notation. The housing market. Oh, T critical values? I love that. Okay, getting the question going. Housing market. Here we are. Let's go do it. Music. That is called Sad Chill. I'll have to see which. Let me see. I might be able to see really quick DDO on that, what it is. That song is called, remind me later. Sad Chill is Waiting by Andrew. There we go. I'm just on my downloads. Waiting by Andrew. It's open music that you can use. There it is right there. There's the name of the music. I've got all the music. There's my HackerMan logo. HackerMan. Stat1 HackerMan. There you go. Okay, let me mark this in the notes and let's do it. I play this for HackerMan. Stat 201, chapter 14, homework. Oh my gosh. Chapter 14, homework. The housing market. Okay. The housing market has slowly recovered since the crisis, and we have a bunch of things right here. The sample showed that the average person lost $8,472 with a standard deviation of 1,814. They talked to 33 potential buyers. Okay, so what's the notation? Noel, help me out. Tell me any of the notation for this problem before we get started. What is any of the notation? What do you see? Once again, if you're watching this video, give it a try. Try to find the notation. The better you can find it without my help, the better you'll do for the test. I will show you all the answers, but take some tries at it. Don't worry about being wrong. Write down what you see. If you write down wrong, then remember. And you'll be like, oh, yeah, I got it wrong. It's nothing wrong with getting things wrong. Get it wrong, get it right. That's what we do. You are correct. Sample size. Got the sample size. No, that's not sample size, though. There is a sample size. So sample size wouldn't be in dollars. Let's throw you some points right there. Good try. That's not the sample size. That's not the sample size. There is a sample. Yep, there we go. Sample size is 33. 33 bids is the samples. Yes, nice job right there. There's another thing we can find from that. Keep going. What else do we see? I'll give a huge hint after the next guess. Don't worry about being wrong. This is a confidence interval for the true mean, chapter 14, to estimate the true mean housing loss. Ooh. Didi, you're super close, and Noel's kind of closer. So since this is from Didi, you're super duper close. We're going to throw you 5,000 points. So you're kind of right, but it's a very particular thing. And some equations might write it like this. If you look at a lot of statistics books, they'll often use this notation. We won't. I'll change it in a moment. So you're kind of right, but there's a small, very important difference. So mu means the true mean, and sigma means the true standard deviation. Since these came from samples, this is the sample standard deviation. Oh, that's variance. It's not variance. This is the sample standard deviation, and this is the sample mean of variable y. You can call it x. A lot of textbooks call it x bar, and it's just the sample mean of variable x. It's just a name, so the average. That is the average of whatever we're trying to look at. You can call it the variable x, you can call it y. It's just, you can call it L, N, whatever you want to call it. But that is, so when you write mu means the true mean, and when you write sigma, it means the true standard deviation from the full population size. So N is related to these because they come from samples, but population would have a population mean and a population standard deviation. Does that make sense on the small difference right there? The point of this interval is going to be to estimate the true mean of the interval. Yeah. And so you're right. It is standard deviation. It is mean, very nuanced. It's the sample mean, the sample standard deviation. And if you notice, the only thing we're missing from this interval now is what? DD Noel, what is the only thing we're missing? What is the only thing we're missing? We got something in here that we're missing, where everyone gets stuck on these intervals. The T. Now, the T comes from William Gossett. He worked at Guinness Beer. And Guinness Beer. William Gossett. So here is his plaque, William Seeley Gossett. Here, I'll paste it in here. Copy image. No, I don't want copy image. There we go, copy image. William Seeley Gossett, Guinness Beer, chief brewer and statistician, student tea distribution. There it is, the student tea. He called it student because he wanted to use a pseudonym, so he called it the students. So student was the name of the person who like published the work. It was work by student. And T, maybe he's William Seeley Gossett. I don't know why. Maybe because T's the last letter in his name, he picked T. But he called it the student tea distribution. And what is it? Well, it's basically the normal curve. It's basically the normal curve. Like they got a bunch of cool pictures. There's all these people always pointing out that it was made at Guinness Beer. And it's basically the normal curve. The big difference I like to point out about it is Mr. T comes in and he smashes it down, because the T distribution always has with it what are called degrees of freedom. If it has very low degrees of freedom, it's smashed down. If you look at that right there, Mr. T came in and said, "I'll pay the fool." I called it. And then as it gets more degrees of freedom, it rises up into the normal. And you can see that classic 1.96, which we could do for a 95% confidence interval. It was 5% outside there, but we can do 95% inside and see the classic 1.96. Even better yet, if you have 60 degrees of freedom, the T is actually 2 for our 68, 95, 99.7. The T is always going to be larger than the Z. It eventually approaches the Z, but you can see right here with it all smashed down with no freedom, the T is much larger than the Z. And so for those wondering, the T is used for a finer calculation when we have smaller sample sizes and have not truly estimated the variation within the data due to underestimating the standard deviation due to a lack of understanding of outliers. Basically, when you have a small sample size, you make your intervals wider. Why do you make your intervals wider? Because you probably didn't capture outliers that would increase standard deviations. And because you've improperly estimated the standard deviation, you do this like fudge factor, which makes your intervals wider. Do you notice how this is wider? And then if we get a bigger sample size, the interval gets tighter. Now I'm saying sample size, but the sample size dictates the degrees of freedom. What are the degrees of freedom for our interval here? What are the degrees of freedom? So solve the degrees of freedom for our interval. T is basically Z. T is basically Z. T determines is based on how confident we are. So it's basically your Z for this interval. When used for intervals, T's can be used for tests also, but T comes from the T distribution used to, when making intervals, determining the level of confidence will tell you the T. We do use the applet, So here's how we do it. Every T has with it degrees of freedom. The degrees of freedom tell you the shape of the T. So that's huge notes. Note number 1, every time you have a T, it has degrees of freedom. Know that fact. Note number 2, the degrees of freedom formula is often given for you, especially we'll tell you on the test. Note number 3, we have confidence intervals that use a T based on how confident they are. So first question I ask you is, what are the degrees of freedom for this T? What are the degrees of freedom for this T? So the degrees of freedom are found in a formula right here. That is the degrees of freedom. That's DF, that's DF. What are the degrees of freedom? What would the degrees of freedom be? Well, there's the formula, n minus 1. So we solved the formula. It's 30. Yeah, that's all it is. So now you go back to your applet, which the T applet can be found right here. Spanbauer, oops, didn't do the exclamation T. Spanbauer created our own T applet. Really love it. I use other distribution applets too, but Spanbauer put them all in one spot so we could use different applets. Huge shout outs. Really brilliant guy. I'm Spanbauer. Here is his T applet. And we put in 33 degrees of freedom. And then we go between for a confidence interval. And then the question says, we'll eventually find out the percent confidence. So we can't solve it yet because we don't know how confident we want to be. But notice how when you put in different degrees of freedom, the shape of the T changes. It's more apparent with smaller degrees of freedom, but the shape of the T will change based on the degrees of freedom that you have. And we're up here at 33 degrees of freedom, which will dictate the depending on how confident we are, the t-score used to make the interval. Is this making sense, Noel? Ask questions if you have it. Let's look at the first condition right here, what they want us to check. The conditions for a t-interval as follows. Random, 10%, and nearly normal. So since these are randomly chosen, we would assume they're independent. What are the degrees? Oh, DD, good question. I'll answer that next. The data are assumed to be independent, and from a normal population, check the assumption. No. They assume to be sample size large enough. Data are assumed to be independent and from a normal. Check the independence with randomization. Check the normal population with the nearly normal using histogram. That looks correct. We don't do successes and failures here. That's obviously wrong. And we wouldn't check independence with nearly normal. No, this looks to be correct. Good. There we go. And so DD asks, at what point do we move from using the student t instead of the standard normal? When are the degrees of freedom considered high enough? Probably around 100. And so here's the really, really great thing. So if you go to a t-table, so t-tables are basically collections of the values. So we're going to copy one in right here. It's a really good question. Because back in the day, or maybe you've seen this, DD, that people have t-tables right here, where what I would have to do is say, I want a 95% confidence interval, which relates to 5% on the outside. So a 95% confidence interval with 95% in the middle would have 5% in the tails. So this amount right here, when it says two tails, it's talking about this amount right here, that 5% is left over in the tails. So that would be the proper t-score for 95% confidence. And then we'd go down here to 32 degrees of freedom, which you notice is not on here. So on this table, what you would go to is the closest one, and you'd go to this right here. Because we don't, or you could kind of be like, maybe it's about 2.04 or so. Because notice it gets closer to 1.96, which is when you have infinite. So it's showing you approach the z. So what has changed about the world, so there's 2.042. The actual answer to this is going to be 2.035. Oh, we have 32 degrees of freedom. There we go. 2.037. And we can carry more decimals on it. So that's kind of neat. I like that repeating 3 for a moment. So with applets nowadays, you can get the actual t-score even if you have something crazy like that many degrees of freedom. Notice it's not quite 1.96. It'll actually approach 1.96 as you get more and more degrees of freedom. So it is a limit. And a lot of people say the t and the z are virtually identical after, you know, maybe it just keeps getting smaller towards 1.96. Oh, I was going the wrong way. But it'll keep approaching 1.96. And actually, here's the fun fact. 1.96 isn't even the actual z-score. It's 1.95996. It's just everyone rounds it to 1.96, but it's 1.95996. And there's the more decimals. So it'll approach this number, which is the actual z, more commonly said by statisticians 1.96 when rounded to 2 decimals. So there is no point at which the t becomes the z. It's usually after maybe 100, or this table says kind of after 1,000, just use the z. The decimal differences are so minute at this point that you're down to the 3rd decimal difference, or you'd be into the 4th decimal difference after 1,000 degrees of freedom. So it's like, it doesn't really matter. And for calculation purposes, I'll usually, and I love it, I mentioned this earlier, I'll usually just times by 2 for a 95% confidence interval. It'll have problems with the decimals, and then software will do the exact calculations in the background. So if you're doing it via software, it'll do the exact t-score. Very few, I've never seen anyone use a t-table in practice. Like I've never seen a statistician be like, let me pull out the t-table. Everyone just lets software do it, or you can get the exact, t-score right here. In the 32 in the degrees of freedom is the n-1. That is correct. Great job, Noel, right there. So 32 goes right there between, and we go to another decimal, 2.037. There we go. So that means we have this value. And this t will be 2.037. The mean is 8472 plus or minus. There we go. There it is. All we have to do is solve the formula. Once again, it really boils down to notation. So 33 square root. We'll clear everything. 33 square root. 1814 divided by that. That is the standard error times by 2.3. Ooh, there we go. That is the margin of error So 643.24. There we go. Is it making sense, everyone? DD Noel, is it making sense? I just found, I always go and find the margin of error first. That is not N anymore, so maybe I should erase the coloring right there. I go and solve the margin of error, and now that I have the margin of error, we get the lower and the upper. So the upper is going to be 8472 plus this, which is 9115. And then we go subtract it. We go 7828. Ah. Nope. 76. And there's the bounds. So the lower and the upper are either I was not sure what to do. T. Yes. It's once you understand these problems, they get really simple, but it's the understanding. It's a process. It's like you have to work a bunch of them and be like, oh yeah, the T is based on this. So I'm going to go out here. I'm going to enter it off the screen, and then because that way I can look at it and do it. Round to the nearest whole number. Should have looked at that earlier. Okay. Check answers. What? What did I do wrong? What did I do wrong? Check my work again. What did I do wrong? S or square root N T 8472. You find the error, I'll be very, very happy. Let me check my math again on the margin of error. So 33 square root. That's that. 8472. That's right. 7829. Oh my gosh. I can't type. I can't type. So here's the fun thing. DD Noel, are you still here? I really like these questions because the T is always bigger than the Z. So let me put these. I'm going to do this last one for fun right here with a little bit of time. Yes, good to see you, Noel. Hopefully, these are my favorite type of questions. Because if you understand the T curve, you can solve these questions without using the applet. See, it says using T tables, software, all these things right here. This is probably about 2.74. Sure. 2.78. Nice work. 61 degrees of freedom. Oh, I know what that is. That's 2. There we go. How in the world? So it goes to the concepts I talked about. The z-score for this is 1.96. But with lower degrees of freedom, the T is going to be wider out. So I know this can only go as low as 1.96, but that would be infinite degrees of freedom, or like 1,000 degrees of freedom is basically 1.96. I also know at 60 degrees of freedom, it's 2, and we just did one with 32 degrees of freedom, and it was 2.04 basically. So now it's probably about 2.08 because it's going to be a little bit bigger. Remember, we just did a problem where it was 2.04 with 32 degrees of freedom, so we got it right. 99% confidence is 2.5758. This is pretty high degrees of freedom. So I know the z-score off the top of my head is 2.5758. The T is always wider. And as we get more degrees of freedom, it approaches the z. This is a pretty high degrees of freedom. So we're only going to go a little bit higher with 62. And we check it. We got it right. So this one right here is 90% confident. The z-score is 1.645. I'll show how I'm doing this, or how you can get the right answer every time. Well, but Noel, this one's not tough though. Noel, I want you to find the exact answer. I'm gonna take a guess, but I want you to go to the applet right here, and on the applet, so anyone who's like, how in the world? Go to the applet I just loaded up right there. You'll see it on the screen. And with the applet, tell me the right answer. What is the T-score for a 90% confidence interval with 80 degrees of freedom. This is actually a tough one that I'm probably going to get wrong. So that's the z-score. So the t has to be bigger than the z. This is pretty low degrees of freedom, so I'm guessing 82. I got it wrong. I thought I might get that one wrong, but what is the answer? And then I'll show how to get the answer. So see if you can get the answer with 18 degrees of freedom. What is the t for 90% confidence? So go to the applet right there. Hit the between button. Hit the between button. Make sure you've clicked between on the applet and tell me the answer when you click between. So click between, and what does the between say? So make sure you've clicked between. And then what does the between say? And I'll show what you probably found, because I think you're right there. So you have 90% entered in, 18 degrees of freedom. Was it that? Really? Well, there you go. You did it. So as Noel just did right here, you go to the T applet and you say, I want to go between and cover the middle 90% of the curve and do 18 degrees of freedom. And there's the answer. That's how we're doing it. I mean, you don't have to memorize it like I've memorized it, but you can just get the answers to it. So the next one right here, you might even get it quicker than me. The z-score, which will stay the same, is 2.3263. And this is only going to be a little bit bigger. I would guess 2.37. What is it, Noel? 2.37? So what is it? I'm guessing 2.37. 2.37 seems about right. Am I right? 2.38. There's a little bit of a fudge factor there, so it gave it to me. So you can just go to the T applet and enter in, how many degrees of freedom was it? It was like 98 degrees of freedom. No, it's like 72 degrees of freedom or something. 72 with 98% confidence. And there it is right there. So 2.38. And that's how you can get the, so that first question is like, and we don't put things like that on the test, but conceptually understanding, because remember, I know the 2.3263 because that's with like infinite degrees of freedom. You get 2.3263, even more degrees of freedom will approach 2.3263. Because remember, the T approaches the Z as degrees of freedom are higher. It's harder to get it when the degrees of freedom are lower, because that's when the T and the Z are most divergent, because the T is more spread out for lower levels of degrees of freedom. So the T is a more exact way to make your intervals that William Gossett made while working at Guinness Beer. They published in Biometrica, I think. Is there a way to solve it on? No, we would just conceptually, the T has thicker tails. It's more condensed in the middle technically too, but it has thicker tails, it has more area in the tails. And I really like the stat distributions applet that shows that. It's just the way this applet shows it, I think it shows better how it has more area in the tails at lower values of degrees of freedom. You can see the thicker tails, and if you go to higher degrees of freedom, the tails get thinner. You can see between -3 and 4, -3 and -4. Now there's more area, and there's less area, and it approaches the normal curve. So we just go with conceptual knowledge. We do not have you find the T. We do not have you use tables. And with that, I have a meeting in about 1 minute. Bye for now, everyone. Noel will be back at 10. See you then. Bye.